Yeah, I mean, I'll just intro a bit. So, hi everyone. This is the next day, next lecture. We're going to be talking a bit more about groups abstractly, connected a little more to symmetry transformations, and then we're going to introduce our ideas for classical mechanics. Okay, but first we have a question at the beginning of this.
Yeah. So what is the difference between a group and a set?
Yeah. So this is a good question. And there's a sort of more general question you can ask for all of math, which is, what is the difference between a set and then these these things with more structure that we actually care about? So a set by itself is just the collection of the elements. And the group, some people read it like this, is you're sort of taking together the set in which you get the elements that you put the operation in. So we had G, right? So your domain for your operation was G cross G. The range was G. So that's the set that you put into the operation. And then you consider it with the actual operation. And then you say that this whole thing is the group. But often for simplicity, if we're referring to this group, we'll just write it as G. And we'll say like a group G. And hopefully it's understood what the operation is. Sometimes you can deal with multiple operations, and then it's better to put this whole thing to state what group you're talking about.
So a group includes a set and an operation that is performed on the set.
Yeah,
Okay.
Exactly. Okay, so the first thing I wanted to do was do just a little bit of an overview of yesterday and make clear the connections between this sort of abstract group language and then what we talked about with symmetry transformations. So have this thing with groups and then symmetries. Okay, so the first thing is that with a group we have this operation that maps from G cross G to G. And so what this is saying is that we can take two elements of G, combine them through the operation, and then we get we get something that must be in the set G. Okay? The statement that corresponds to this with symmetries is that if we have two symmetry transformations, so phi 1, let's do phi 2 compose phi 1. So if you've seen the video on compositions, this makes sense. Have you seen it?
No, I don't recall that was posted on
Okay,
the
it probably
blog
wasn't
site.
linked there, but it's on my channel.
Okay.
But what this means is that, let's say you put something into here. What this is you map x through phi 1, and then you map it through phi 2. So this is what I was talking about when we were like compounding symmetry transformations. You do one symmetry transformation, and then you do another.
Sure.
That's also why I chose to write as phi 2 compose phi 1, because this is the order that indicates things are happening. So it kind of looks reversed, but really it's because this happens first and then this happens.
Yeah.
As opposed to here, people just prefer to put the 1 and then 2. Okay? The point is that the operation between symmetries is the composition of the functions. And this statement that that evaluation of the operation is in G here is equivalent to saying that it is also a symmetry transformation. Okay? So this kind of looks innocent, but it's actually a big deal that it stays in G. Okay. The next thing is that there is an identity element. And so this element, whenever you do an operation of let me just write it out. Whenever you do something like this, it just gives back the other element that you put it into it. Okay? So that's why we call it 1. And here, for symmetries, this is the identity transformation. So this is the transformation that just does nothing. And then, right, associativity is essentially the same between these two. So here we had this G1 times G2 times G3 is equal to G1 times G2 times G3. And for this, it looks like this. Okay? This is a property that's actually true of functions in general. As long as, what needs to be true for it to be able to compose two functions together, and hopefully this is kind of clear, that the range of this function must be the same as the domain of this function. That otherwise, you could get something out of here that you can't put into here. So for this all needs to be true. When the domain and range of the functions are the same, then you can obviously do it.
Yeah.
So this would be like, in this case, it would be like from G to G and then G to G and then G to G, if you interpret these as functions. Which I won't do right now, but in a bit. Okay. And then the last thing is the inverses. So for groups, we're saying that each element of the group has an inverse element. So an inverse element is something that when you combine these two in the operation, it gives you the identity. And there's a reason I'm writing both of these out, and like I said before, it's because we don't know that this operation is commutative. Okay, so some examples that you should be familiar with. In literal multiplication, this is called the reciprocal. We could also call it the multiplicative inverse. For addition, this would be a negative, because the identity element in addition is 0. Does that make sense?
Sure.
And then for symmetries, this was our condition that every symmetry transformation must be invertible. So for all, let me just write this a bit informally. For all symmetries phi, there exists an inverse function to phi that I call phi inverse. So this satisfies the condition here. So like I mentioned before, these two statements are basically saying, we go through the function, go back, and we get back to exactly where we came from. That's the identity function. Okay. So another thing I want to mention is that yesterday I said something about rotations not commuting and then said a bunch of complicated sounding stuff, which for quantum mechanics that was all fine. For classical mechanics, the interpretation is a bit easier. Hopefully we're going to see later this week why this is true, but the fact that rotations don't commute implies that if you take a particle, moving around some point, it has some angular momentum. If you instantaneously rotate that particle in a direction that's different from its angular momentum, then the angular momentum changes. Okay? So that might sound pretty obvious. Something to think about is that if you rotate it in the same direction, the angular momentum does not change. Sorry, so you're rotating about the axis that is the same as the direction of the angular momentum. Then it won't change. Contrasting this, if you consider a particle moving in space, it has some normal momentum, like linear momentum. If you then instantaneously translate it, don't move its velocity or anything, then the momentum does not change. It's the same. That actually has to do with the fact that translations in different directions do commute with each other. And that we'll also see. Okay. So, next thing, we are going to talk about maps between groups. So this is what mathematicians call structure-preserving maps. Okay, and the basic idea here is that every group has an algebraic structure in it based on its operation. The details of that operation are what determine the structure of that group. So a pretty simple group that we could work with is, we usually use angular brackets to denote a group. If we have -1 and 1, and the operation is multiplication, then we can go ahead and check all these. If you multiply 1 with 1, it's 1, so it's in here. If you multiply 1 with -1, that's -1, so it's still in here. Multiply -1 with itself, that's 1, and we're all good. We have an identity element, it's 1. We have associativity because multiplication is associative. And we have inverses because the identity is always the inverse of itself, because if you always have this for any group. And then -1 is actually also the inverse of itself, because -1 times -1 is 1, which is the identity. So all of these things kind of, or no, that's not what I want to do, give you the structure of the group. This is what we would call the multiplication table for a group. There's actually a better visual representation, which looks more like a traditional multiplication table. So you have 1, -1, 1, -1. And if you multiply these out, you get 1, -1, -1, 1. Okay. So this tells you in every possible bit of information you could want what the structure of this group is. But this is not the only group that has this sort of structure. If you think about, now, you take 0 and 1, and the operation is addition. Have you heard of modular arithmetic?
I've heard of it before, but I'm not familiar with it.
So what we're going to do is we're going to add these elements, but we're going to consider the remainder when dividing by 2. Okay? So here we would get 0 plus 0 is just 0.
Okay, yeah, it's coming back to me now.
Okay, okay. So
this would be mod 2 of the function, or the group 0, 1 in addition.
Yeah. So the operation is addition mod 2. Mm-hmm. And if you're not familiar with this, if you're familiar with binary, it's the same idea, mm-hmm. but you are only looking at the first digit. Also, it's related to AND and OR gates. So addition mod 2 is the same as an OR gate. Or sorry, non-OR gate and XOR gate.
Yeah. I was turning that over in my head like, what about 1 plus 1?
Yeah. So 1 plus 1 is 2, but the remainder when divided by 2 is 0. Okay? So if you compare this, well, we have the identity element is 0, right? So let's say this is multiplication. This is addition. 0, 1, 0, 1. This is what we get. So 0 serves the same role as 1, because it's the identity element. And then this other element, it also serves the same purpose. It's kind of this self-inverse, right? And so if you think about it, all we're really doing is going from here to here. We're replacing this multiplication sign with an addition sign. We're replacing the 1 with a 0. We're replacing the minus 1 with a 1. And we get the same thing. So if the only difference is what we label stuff, there's not actually any mathematical, significant difference, then it's perfectly reasonable to think of these as the same group. Thoughts on that?
I mean, with the set that you put in the group, it makes sense, but then you enlarge the set any farther and it kind of falls apart.
Yeah. So when you make the group larger, it becomes harder, but it still happens.
Could you give an example of that, perhaps?
Yeah. So I just wanted to say for one last thing, you can also go the other way, and that's pretty important. Okay. So well, I mean, I guess I brought up one example before, but I didn't show how it works, which was that the rotational symmetries of the dodecahedron is isomorphic to A5. I also didn't tell you what A5 was. But another thing we could talk about is what's a good example?
I mean, is there a way to relate addition and multiplication beyond just the groups -1, 1 for multiplication,
Actually, yeah.
0, 1 for addition?
There's a pretty cool one. So if we talk about our first group is the real numbers with addition, our second group is the positive real numbers with multiplication. Do you know a function that sort of takes the addition of numbers into a multiplication?
I feel like you'll tell me and I'll kick myself for it, but I can't remember.
Okay. So what I'm saying here is that we want a function. This isn't going to help you, but I'm just being more explicit. Let's call it f. So this is the domain of f. That's the range of f. For all x, y in the reals. F of x plus y is equal to f of x times f of y. So the idea is that, like that, previous example, we're replacing x with f of x, y with f of y, and replacing the addition between x and y with the multiplication between these two. Okay? So before I talked about f as kind of like mapping, in these scenarios, we're thinking of f as a way of identifying elements between the two sets. So treating them as almost saying, these are actually the same in the way that we care about. We're just calling them different things. Okay? But back to this. We want to find a function that does this. And it's something you've actually worked with for a long time.
Is it a logarithm?
Close.
If you flip the plus and minus.
Logarithm takes multiplication to addition.
Yeah.
Right?
So it would just be an exponential?
Yeah, exactly. So an exponential, let's make our life easier and talk about e to the x. E to the x plus y, that's that, is equal to e to the x times e to the y. And this is something, maybe not with e, but since like middle school?
Yeah, maybe middle school.
Yeah, that you've learned and used and abused. And so it's not just some property, it's actually crucially important. Because what it serves to do is identify this group with this group. And one thing that you can prove, I think it takes a bit of calculus, but you can show that this function e to the x is invertible, and in fact you know what its inverse is. It's the natural logarithm of x. So the fact that it has an inverse function means that this function is invertible. So not only can we make this identification this way, we can also do it the other way around. Okay. So that's what allows us to say that this group really is equivalent in the sense of groups to this. Okay? It might be more conceptually weird to think about that than the previous one, but it's true.
I'm actually a little familiar with that logic when you're thinking about infinity, for instance, right? Infinity plus infinity, still infinity.
Right.
Or infinity times infinity, that's still infinity. And you can kind
Yeah.
of map that out where like all the positive integers multiplied gives you the same scale of infinity as all the positive integers added.
Yeah, that's true.
So
And
is that kind of the same logic?
that's like
You can
one
map one
part
to
that
one?
goes into it.
Okay.
Yeah. So that thing, it probably has to be true. I mean, you could also do e to the minus x, where you're then mapping negative infinity to infinity, but it's really just flipping it around.
Sure.
What this does, it's more powerful than that because it says, if you move along the number line in addition, a bit of spacing, and you keep doing that, then what happens with the positive real numbers is that if you consider the distance from 0, each time you do that, it gets stretched out by a certain factor. Or that would go even more, actually. It would be like a geometric.
Mm-hmm.
That's what this is saying. Because every time you multiply the same, like you add another a and then 2a and then 3a, that factor of e to the a keeps multiplying this. Okay? All right. So this thing, where this function is serving to identify elements of the domain with elements of the range, and then saying the operation in this set tells you if you have two elements in here, how do I combine them? In the range, you then have two elements here, f of x and f of y, and the purpose of the operation here is to tell you how to combine these. That is the only purpose of the operation. It tells you how to combine two elements in the group, and basically the rules for doing that. So this is f of x times f of y. If we can, find this function f that basically says these are the same and these are the same, and the way you combine these ends up being the same, so that this element x plus y maps to here as well, then it's saying that what the operation is doing in each set is exactly the same, because it's true for any x and y you pick, and then also true for any f of x and f of y you pick if the function is invertible. Okay, so does it make sense now why this is saying that they're equivalent as groups?
Yeah.
Okay. So without the invertibility part, actually, never mind. Let me say it's invertible for now. This kind of function is called an isomorphism. So these two groups are not literally equivalent, but they're equivalent in their group structure. And that's what we care about. The labelings, the symbols we give to them, to the elements and the operation, are not important. The actual details of what they do are. So an isomorphism then gives us a way of saying these two groups are equivalent. And if we have an isomorphism between groups G and H, we say they're isomorphic. And that is an equivalence relation. So I haven't talked about equivalence relations yet in detail, but basically they're relations that have the same idea as equivalence. All right. Sometimes we don't want two groups to actually be equivalent, but we can find these sort of structure-preserving relationships between them. And so this is still true, but we don't necessarily need the function to be invertible. So if only this is true, then we say that the function is a homomorphism. Okay, so one example of a homomorphism. Yeah. So I don't know if I could explain well why exactly this works. But if you consider the symmetries of a square, so yesterday I just talked about the reflective symmetries, but there are also rotational symmetries to this. You can rotate about the center 90 degrees. You can do that 4 times. And so if you think about the set of symmetries that this square has, there are 8 elements to it. Essentially 4 rotations and then 2 reflections for each of them. And so you could then map that group. So that group we call D8. The D stands for dihedral. I don't remember why it's called dihedral. To then just the group of rotational symmetries that this square has, which is technically called Z4. And so what's happening is that there's this sort of structure with the reflections that is being like subsumed through the function. And so whatever kind of distinction you can make between a particular rotation and then its reflection just gets destroyed in going here. But what you get is still this sort of structure preservation of the rotations. Okay? there are probably better examples, but I just can't really think of it. I mean, one actually good example is that you can have the integers with addition, and then you can go to this. So z is integers. Again, weird, but you can then go to this thing, which, is that how they write it? I don't know. So basically this is the integers, but addition mod n. So now you add integers, but then you take the remainder when dividing by n. And the elements of this are basically, they're sets of all these integers that have the same remainder mod n. And this is what you write it like. You don't need to remember this, but this is just an example. So some part of the addition structure here gets preserved into this when you do it. Because you'll find that if you add two integers, their remainders when dividing by n get added. Think about it for a bit.
So you divide two integers, and the remainder of dividing the sum. Yeah, okay, that makes sense.
Okay. Yeah. I mean, I could prove it, but
That's intuitive enough.
okay, good.
At least for me. I'm not sure about the people at home.
Yeah, just think about it for a bit. If you're really stuck, look up Euclidean division on Wikipedia. I'm sure it explains it all. Okay. And there are more complicated homomorphisms that are useful in in quantum field theory and stuff, but maybe we'll get there, but probably not. Okay. What time is it? Oh my god. So, right, last thing I want to talk about with groups is then one last connection that we can make with symmetry transformations. So we took some of these properties that I just erased from symmetries and then made these axioms for the group, right? So you can ask the question, well, why these properties? Maybe there are other ones. And the answer is really, well, we thought of groups independently, and then after, I don't know how long, but years, decades, we came up with these axioms as our sort of bedrock for groups, and we got a whole lot of theory out of it. And we found that this is what we need to make things nice. And then they are also true for symmetry transformations. But something that people came up with when studying the theory of groups is the idea of a group action. And so we'll talk about what a group action is. Those symmetry transformations, they're particularly functions. They're functions of things, right? Usually, particularly things to themselves, right? So when we had the symmetries of a square, you could think about it as these 4 points. And so you're acting on this set of 4 points, and then what you return is again the set of 4 points. So here we'll have the action of a symmetry on the object. And with groups, we have this thing called group actions, where if you just start off abstractly thinking about a group, sometimes what you can construct is a family of functions such that you have basically each element in the group has this function associated with it. It's actually an invertible function. So phi sub g from, let's say, some set A to A and we denote this, phi g mapping A somewhere as this sort of g dot A. So what we're going to do is for the actual group operation, we'll just not write the dots, just like this. So g1 times g2, we'll write it like this. For the group action, we will use the dot. Now the conditions that must be satisfied by a group action are, one, that the identity element acting on any element of this set is just the identity function. And the other, that if we repeatedly do this group action, it's the same as just doing the group operation, these elements, and acting on here. Okay, so this is pretty abstract. But how you can think of this is that you can see that there's the algebraic structure here with the group, and then it expands into this sort of larger structure here. This thing here, G1 acting on G2 acting on A, is the same thing as this phi G1 composed with phi G2 acting on A. So actually what this statement is saying, and this is also for all A in that set, this statement here is saying that the composition of these two invertible functions is equal to this. So written the other way around, you can kind of see the comparison with this. So this is like this.
Mm-hmm.
This is like this. So what you have is a homomorphism from the group G to the set of, or no, I'm not going to use that word, not yet, until you've watched the videos, invertible functions from A to A. So these phi sub g functions, these are all elements of the set of invertible functions from A to A. And we have this function that maps every element of G to such an invertible function. And then it satisfies this property that makes it a homomorphism. So this is an incredibly abstract concept.
Mm-hmm.
But this is exactly what happens with symmetry transformations. That we can think of just the symmetry group and it naturally has this action on what it normally acts on. Or I'll say it acts on the object with the symmetries. So the object that has these, symmetry properties. So we could think about abstractly this group D8, that's the symmetries of the square. And then for each element of that group, we can actually think about the action that it has on the square. So for example, an element of this group would be the rotation by 90 degrees. And we could think about how that rotation actually maps each point to where that point ends up. you could do that then for all the elements of the group, and then that whole consideration is giving you your group action. So, yeah, this is kind of the end of the connection between symmetries and groups. So realizing the last bit, or the last aspect of what a symmetry is and connecting that to group theory. Okay? This is actually one of the most important applications of group theory to physics, because pretty much every way that we'll think about groups in physics is through symmetries or group actions in some way. So in particular, we'll end up talking about representation theory at some point, hopefully, and that is a particular instant of group actions. All right. So let's, in the last 15 minutes or so, introduce some classical physics. So what you're familiar with at this point is primarily Newtonian physics. And in that formalism of physics, we deal with particles. Often we treat them as point particles, and when we don't, we usually consider their center of mass. So we do treat them as point particles. So we have these sort of point particles moving through space, and then they potentially could be under the influence of forces. Those forces usually arise through interactions with other particles. And pretty much the central guiding principle of Newtonian physics is Newton's second law, which says that the force acting on a particle is equal to the mass of that particle times its acceleration. Okay, we're going to introduce a little bit of new notation. This is actually a notation that Newton came up with himself, which is that you're used to saying, acceleration is the derivative with respect to time of velocity. Velocity is the derivative with respect to time of position. He actually used different symbols for these. So if you're talking about, let's just say in the x direction, that the velocity in the x direction, so dx by dt, he wrote as x dot. And then the acceleration, which would be the second derivative, was x double dot. And you could go on and on and add more dots. Usually this is all that we need to work with. And then you could also do with the arrows. I think it gets kind of messy, but like for Newton's second law, we would have to do it. And this would read, let's say you use r for the position vector. Or I guess you're more familiar with x as the position vector, maybe?
Either one.
Either one? Okay, let's use r. And then we have mr double dot, which denotes the second time derivative of r. Okay. This is basically what Newtonian physics boils down to. There's the first law and the third law, but more or less they correspond to exactly this. Okay, Newtonian physics is fine, but sometimes it's hard to deal with complex systems thinking about all the forces that are involved in it. So one kind of common example is the double pendulum. So you have a sort of fixed ceiling, then you have this fixed point where you have one pendulum. This has a fixed length L, and then attached to here you could have another pendulum that also is L. Let's say these have the same mass. This is a very difficult system to work out the equations of motion from here, and it's impossible to solve the trajectory analytically. This is a classic example of a chaotic system. So one reason it's very hard to work with Newton's second law here is that you have to deal with all of these tensions and stuff like that. And it's a bit messy. So one way that you've sort of avoided using forces in the past is through using energies. And that's pretty useful. I don't know if it can be applied to this exactly, but that's where we're going to sort of take inspiration from a bit. I have 10 minutes. Awesome. So the formalism we're going to talk about next is what's called the Lagrangian formalism. And the point of the Lagrangian formalism is probably not clear if you haven't seen this before, but I think where Lagrange kind of got the inspiration from is working on problems where you're trying to minimize a quantity that comes out of an integral. So in this case, what we're going to have is something called the action, which is equal to the integral from, let's say I have two endpoints of time. So a to b is a time interval. You're going to integrate a quantity called the Lagrangian over time. And the idea is to minimize, or really just extremize, the value of the action. So this Lagrangian will depend on properties of the system that you're working with. And this seems kind of random, right? We were talking about forces and differential equations, and how are we now getting to this integral that we want to extremize? The answer is that, people like Euler and Lagrange studied these kinds of problems. This is not the only problem like this. And what they saw is that what you always get is a set of differential equations for this quantity L. So what I might do, I'll either derive it tomorrow or I'll do a video at home today. But if you say this thing depends on the position as a function of time, it depends on the velocity. It may also depend explicitly on time. So if this is like an open system, that could happen. The condition that this is extremized is that the partial derivative of the Lagrangian with respect to x is equal to the time derivative of the partial derivative of the Lagrangian with respect to the velocity x dot. Okay? So these are called this is just one equation. When you have multiple variables, you get one for each position variable. And those are called the Euler-Lagrange equations. And the idea is that, well, this is a set of differential equations. This is a set of differential equations. If we can sort of match these up, find a Lagrangian that makes this the same as this, well then, instead of talking about this kind of physics, we can talk about this kind of physics. And that seems a bit random to introduce, but actually there is a lot of payoffs that come from this. Most notably is the idea of Noether's theorem, which tells us how to use symmetries of the Lagrangian to tell us what the conserved quantities of the system are. So, yeah, that will then tell us about things like translations being related to momentum, rotations being related to angular momentum, time translations or time evolution being related to energy, and a bunch of other stuff. And that is also connected to what I was saying, that rotations not commuting tell us that if you rotate the angular momentum in a different direction, then it changes the angular momentum. So these are all kind of related. Noether's theorem, and then a bit more complicated mathematical structure called Poisson algebra, which hopefully we'll get to talk about in a few days. All right. I don't think there's a lot more I could say without deriving this, and I do not have nearly enough time to derive it. So I think we'll just stop here.